So I think we're recording at this point. And one thing I can do for these kind of tricky sections is, again, I can't make it available until this due date's over. I could change this due date to today, then I can move this one out to today. I should be able to. 4.2. No, it would have to be the 29th. Oh, we'd have to make this one due on Wednesday to get this one available today. Geez, that's kind of rough. So the kind of thing that kind of puts me in a corner is if I make the due dates really, really fast, then people kind of miss out. But then if you're working at the pace of the class, you're not seeing section 4.2 until way later. It's a bit of a kind of a lose-lose situation. But one thing I can do with this is I'm going to give this some thought. I might email the math department. I might make the due dates really aggressive and then just put lots of overall extensions. That way people won't have to keep on requesting extensions. And if you're working ahead, you'd have that ability too. Does that sound all right to folks? Okay, I don't want to do it just right now, right here, because I wouldn't want to mess it up on a mistake. So let me make a note on this. Change due dates. So sections show up sooner. Okay, I'm going to work on that the moment I get some available time, probably after office hours over there today. I'll start messing with these due dates. I'll also put an extension on some of these sections for just the whole class. That way, once again, if I put in the due dates really, really quick, you'll still be able to work in that section without losing points. So that's my plan so far. But any other questions or comments at the moment? Okay, thanks for mentioning that. That's one of the things about, again, there's not a lot of freedom to put things the way you would like in ALEKS, and they absolutely don't allow us to have things overlapping inside the system, but we'll find a way to work around it. And I'll probably comment on this again when we come back on Tuesday's class. I'll just set that aside for now. And let's now go back into where we were right about here. And any other questions at the moment, folks, to start us out? Okay, well, I don't have a ton of announcements other than we have a brand new quiz, number 6, but that's probably what you're expecting. This quiz, I forgot what it's based on. Let me take a look. Looks like we're just dealing with linear equations. So I think this problem right here is motivated from section 4.1. It's either the first, second, or third example, somewhere kind of earlier on there, but it's just another one of those really fast kind of quizzes, getting everyone on the same page. I feel like this is the tricky one, so look up point slope form or what we did in class. And part C is not so bad. You're just solving your equation for y, which is usually what you would typically do anyways, so you'd have a function. So that's our upcoming quiz. Let me get back into the course. And try to get that back to where it is. There we go. And I think I'm all out of announcements, folks. Today, our goal is to work through section 5.1. If we finish it today, that'd be awesome. But if we need a little bit more time, we'll finish it on Tuesday. If we look a little bit further into the schedule, we have midterm week coming up, but that's just a chance to say what your grade is in the class right at midterms. There's no exam here. And our second exam is coming up Tuesday, October 17th. Not even October yet, so we still have some breathing room. And around the end of this week here, I'll start posting information, review problems, and those kinds of things under that week here. Well, I think that's our full set of announcements. Let's jump into section 5.1, unless there's any comments at the moment. Okay, well, what we did in section 4.1 and 4.2 is we're looking at polynomials of this form. Degree 1 means there's a power 1 right here, and x is equal to x power 1, so that's what's making this one degree 1. Now we're changing gears and looking at degree 2 polynomials. Degree 2 is because of the power 2 right here, and we'll just call these the quadratic functions, much like we call these ones linear functions, even though they're all polynomials. So jumping into the notes, here's the restatement of that definition. We'll say a function defined in this way, where a is not 0, the requirement there for not being 0 is just so that term survives. If a were 0, then this might be degree 1 or possibly degree 0 if b is 0 as well. So forcing a not to be zero means we have a legitimate polynomial here of degree 2. We'll call it a quadratic function or a polynomial or a degree 2 polynomial. All of those things will be synonymous with that kind of object. And the major thing we're interested in is equation solving. Sometimes this is written in a weird way. So Alex will occasionally ask for zeros of a function, or they might ask for roots of the function, and they mean the same exact thing, either way they state it. What we do is we set the entire right-hand side equal to 0 in this equation. So whatever your function f of x is, equate it to 0 and start solving, and you're getting either the zeros, if you decide to call it zeros, or the roots, if you call it that. But in either case, we're really just getting x-intercepts if they exist. So let's give this a try. We have a function right here. This one's kind of a warm-up, but if you work through the procedure, the notes here, you want to first say f of x is 0, only because they said find the zeros. So that kind of makes sense, right? Set the function to 0 and you're finding zeros. Next thing you do is, on the left-hand side where f of x is, put in the definition of 5 times x minus 3 times x plus 5 equals 0. And this reveals what we really like about example 1. That function is in a factored form. It makes finding zeros very, very easy, because down here, we're just going to use a zero product property. We should state it if we're going to refer to it. The zero product property states if a times b equals 0, so the product is the multiplication, and we call it the zero product property because of the 0 there. If you're working with real numbers, not complex numbers, those ones are awfully strange. But in the real number system, you can have a is 0 or b is equal to 0. Coming back here, if we have 3 things multiplying and resulting in 0, either the first thing is 0, that's impossible, that's clearly a 5, it's never 0. Or the second thing is 0. We can say x minus 3 equals 0. Or the third factor, x plus 5 is equal to 0. So in a fully factored form like this, we just set all the factors equal to 0, then solve the equation. From the first equation, we get x equals 3. And from the second equation, subtract 5 from both sides, and you get x equals -5. Really, we could have just looked right up here. Plug a 0 in, and the whole right-hand side becomes 0. In other words, f of 3 is 0 only because of throwing 3 right there. It wipes out the whole right-hand side. Likewise, if we evaluate f at -5, we get 0 as well, and that's a really fast double check. But we did it, folks. The function was nice because it was in that fully expanded form, and so you can pretty much just eyeball it and state the zeros. If you did that on a quiz without showing these steps in the middle, that would be appropriate, since it's kind of looking at us. Just took the opposite of -3 and the opposite of +5. Any questions, folks, on finding those zeros? Okay, really, the whole purpose of example 1 is just getting through this terminology here. The problem wasn't too major. And now it's asking us to write f of x in its standard form. We're just referring to this right here. Again, really just a kind of a problem getting familiar with the terminology. If you want to take our function f in standard form, well, it'd almost be tragic to do that because we lose a lot of information, but sometimes standard form is helpful on its own. We'll see that in these notes. So let's rewrite this as f of x equals 5 times x minus 3, x plus 5. To get it into that standard form indicated right here by the red dot, we're just going to multiply this completely through, expanding it all. So I'll leave the 5 right where it is. I'm going to open up a new set of parentheses, which will result from FOILing out x minus 3 times x plus 5. So first distribute that x into the x plus 5 group, and we get x squared plus 5x. Then distribute -3 into x plus 5 to get -3x minus 15. Now we can combine some like terms inside the parentheses to get x squared plus 2x minus 15. Last thing we're going to do is just multiply through by 5, and we now have a 5x squared plus 10x minus, let's see, that's got to be like a 75 That's some rude arithmetic for this early in the day, but we've got it, folks. That's our polynomial in expanded form. Any questions at the moment? Okay, the value of this expanded form is occasionally, if we have something like that function there, we want to find its maximum or its minimum if it has one. It might not be easy to do in this format, but in its extended form, we have a formula called the vertex formula, which is going to help us find the maximum or minimum of our polynomial, but it needs to be written in this way so we can see how to use that formula. Then it mentioned our f of x would be of this form with the ax squared, a bx, and a c. Important information is for our problem, a is the leading coefficient, which is 5. B is the coefficient that goes to the degree 1 term, which is 10. And C is the constant term, which is negative 75. We didn't have to do that on this problem, but we're going to be using formulas that just work in the coefficients A, B, and C, vertex formula, quadratic formula. So it's good to spot those each time you put something in standard form. What we did, folks, that's example 1, kind of a quick warm-up problem. Any questions at all in running through this one? Okay, let's try this out again. Example 2 says, write the quadratic equation whose roots are 5 and negative 11, and whose leading coefficient is 5. Now, in a certain sense, this one's kind of tricky unless we have a good feel for what should happen. Let's focus on this part. They said the leading coefficient should be 5. And notice in our problem in part B, the leading coefficient is also 5 right here. And it emerged right there before we started putting it in standard form. So our polynomial down below first takes on this format. It's going to be equal to 5 times something. Now they gave us other information. They said the roots. That's a strange word, roots, are 5 and negative 11. But keep in mind, that's the same as saying zeros. The root and zeros are completely synonymous. On this one, when we found the 0 of 3, we went back here and we produced x minus 3. We put in the opposite value. So here, if our 0 is 5, we can go, let me try again. We can go like this, put in x, and then the opposite of 5. Throw in a negative 5 right there, and we're in good shape. Next, on this one, it had a 0 of negative 5, so it emerges as plus 5 for us. If there is a root of negative 11, we'll just go x plus 11. And that's finally our polynomial. It's a weird exercise because there's not much to do. You're just writing down the formula per the information given, but it's kind of like doing part A backwards. If you're in this factored form, you can find the roots or call it zeros. But if you have the roots and the leading coefficients, you can go backwards and just reconstruct the whole polynomial like that. Honestly, when you see this problem in ALEKS, forget which product we're using. When we see this problem in ALEKS, it's kind of a freebie. Take a look at what we did in example 2, and this one goes really, really fast. Other questions, folks, with getting through this one?
So we don't have to factor it, it's just writing it out. It's just writing it out like that.
Exactly. If you wanted to, you could expand this out to distribute 5 through, but I would only do that if you're told put it in its standard form.
Okay.
Otherwise, I mean, you're still going to get the right answer, but you're taking extra steps, which for me at least is an extra opportunity to make a simple mistake. If this is all they want, that's probably a good stopping point. Other comments at the moment? Okay, so this is the world of polynomials at the moment. For me, the big confusion is the ALEKS system and our book conflates zeros and roots all the same. So keep in mind, both of those are really just dealing with that equation. Now, next thing we're going to do is find the zeros of this quadratic function, and that's it, just find the zeros. This one's kind of scary, to be honest, because the one on top, we found the zeros really fast due to its factored form, but this one's now in a standard form. What we could try is to factor it using, say, the trial and error method. But let me show you what I would do before I even try to factor this. The downside of factoring is if you're using trial and error, which is very, very efficient and fast, Well, it might not factor nicely with trial and error regardless, so it could all be wasted time. So the first thing I would do is work with this object. The discriminant kind of a strange word. The discriminant is something that's going to determine the behavior and number of solutions, number of zeros, if they exist. So the discriminant is this quantity, b squared minus 4 AC. Exactly, that's going to be the part that goes in the square root in the quadratic formula. So if our discriminant comes out like a 25, that means you really don't need the quadratic formula. It's kind of a beast to get through if you have to do it. It's easier to just factor it. But if this comes out as like a 27, which is not a perfect square, or even worse, like negative 13, which will be a negative inside a square root, giving us a complex number, means you probably don't even want to try to factor this at all. So going to the discriminant right away is going to tell us what the most optimal solution is going to be, either factor or quadratic formula. Any questions at the moment about that thing? It's probably going to be quadratic formula if you're guessing, if the discriminant showed up here. But if you're put down in the discriminant, you need to know what the coefficient A, the coefficient B, and coefficient C must be. Anyone see what the values of A, B, C should be in this problem? Exactly. Once we have that down, we're in great shape. Really, that's kind of the major battle right there. This formula is useless unless we know where we're getting all of those coefficients from. So let's plug that into the discriminant and see what we get. B squared minus 4 AC becomes, we're squaring our B coefficient, C to the right. So that's going to be a negative 2 squared coming from here. Minus 4 times A, which is 2, times C, which is 5. So this is going to become positive 4 minus 40 equals negative 36, which is less than 0. So if this happens, that means factoring was not a good idea. There will be 2 complex valued solutions. Only because of that less than 0 right there. If it was bigger than 0, we would have 2 real number solutions. And if it was, say, something nice like a 4, 9, 81, any perfect square, you can just factor that and move through it really fast. And if it turned out to be 0, that means there is exactly one solution to this, a repeated root, we might say. Whatever the case, now that we know we need to use a quadratic formula, we might as well state it. Choose maybe green for this. The quadratic formula is x equals, we take negative b, add and subtract the square root of the discriminant. So that's the b squared minus 4ac. Divide the whole thing by 2a. And I would say for the sake of an exam, this is a good one to have memorized so you don't have to worry about it. But just for extra insurance, I would probably put this on my sheet of notes for the exam, say the final exam. I forget our particular class doesn't have notes on exams. Sorry about that. My other classes do. But on the final exam, we will have a note card. This one would be really good for that note card on the final exam. Well, might as well make a note on this. This is helpful for memorization. Well, we have the quadratic formula. So now here's what we're going to say. It said find the zeros of this function. So we're just solving f of x equals 0. Coming from that statement right there. Everything we did above is just kind of preliminary to it. So we're taking 2x squared minus 2x plus 5, setting it equal to 0. And to solve this thing, the quadratic formula pretty much did it all for us. X is going to be equal to, we take negative of b, look up on our table, that'll be negative of negative 2. If you put positive 2 in there, good call, that's taking an extra step right in the middle. Plus or minus the square root Of the discriminant, this is something that's always a good idea to calculate first. Negative 36 goes here, and now it's really fast to move through the quadratic formula. And finally, the whole thing is divided by twice a. Up here we have a set to 2. And again, this is kind of the purpose of why we had a detour in section 2.4 to talk about complex numbers, because it comes up right there. A square root of a negative can be simplified by going like this. First, let's call that positive 2, plus or minus. Over here where that negative sign is, we'll put in an I, root 36. Or just 6i if you took care of that root right at this step. Whole thing divided by 4. So now we can take the square root of that 36. We have 2 plus or minus 6i divided by 4. And now, well, sometimes these simplify, so we have to keep on going. Let's divide numerator and denominator by 2. You could just put a 1 here, a 3 here, and a 2 here. Or if you'd like to do it the factoring way, it could look like this. Equals, I'm going to factor out 2 from the numerator, leaving 1 plus or minus 3i, divide by 4, and then I'll cancel at this step. 2 goes in here twice, and it just cancels that off entirely. But this is more being really, really safe. If you canceled right here into all terms, numerator, denominator, and just wrote 1 plus or minus 3i over 2, that would have been just fine. But we got it, folks. This is a really strange quadratic function. We did not find any x-intercepts at all, but we still have zeros. Every polynomial will have zeros of some sort, and ours happen to be, let me hide this thing, 2 complex valued solutions on this polynomial. Any questions at all running through this one? Yeah, go ahead.
Where's the I come in this equation?
It came in from that negative right there. And kind of the steps in the middle is if you have a square root of, say, negative 25 or negative anything really, we split that up as square root negative 1 times square root of the positive portion. But then by definition, square root of negative 1 is I. Then it'd be times 5 or 5i.
Okay.
So really, it's that negative right there, producing this I right here.
So I is just another way of writing 20.
Exactly, yes. And just for tying that together, I'm glad you mentioned that. Let me put this in purple and I in purple, just to show where that came from on the notes. Other questions at the moment? Okay, when people write down solutions, especially when they use the quadratic formula that gives a plus and a minus, really there's 2 solutions here. If you leave your answer like this, 1 plus or minus 3i over 2, I think that's just fine. That's a normal shorthand that lots of people use. But then Alex is kind of a jerk. Sometimes they make us write it out by separating out the solutions. Because of that, I'll do it as well. So the zeros are x equals 1 minus 3i over 2, comma 1 plus 3i over 2. Again, just to emphasize, you don't have to do that, but if Alex is making you do it in the homework, I'll do it in the notes as well, so we know it's coming. Well, that one is definitely a weird function. As soon as we get higher and higher degrees, more weirdness does occur. But I'd say the main takeaway with this is, if you're going to find zeros, the best situation is this, a fully factored. If it's not factored, you want to try to factor it. But if you're not sure if it could factor at all, take a look at the discriminant. If you get a negative discriminant, automatically you should just be using the quadratic formula to get through it. Well, that takes care of that example 3 there. Any questions whatsoever, folks, about this one?
So that last part that you wrote for x equals 1 minus 3i divided by 2 or 1 plus 3i minus or divided by 2, are you saying that that's probably the preferred answer for Alex?
Alex wants it that way, yeah. You're really just saying this. That's the shorthand, and I'll always accept that on quizzes and exams.
Okay.
Other questions so far? Okay, well, let's take a look at the further concepts going along with this. When it comes to these parabolas, there's a lot of extra terminology that we have to deal with. I stole this problem directly for Alex, and it's probably a good way to talk about vertex, axis of symmetry, and so on. The parabola that we just were dealing with is like this one right here. It has no actual x-intercepts. So when we go to find the roots or the zeros, we're getting complex numbers. So anything like this is producing those complex numbers the moment the discriminant is negative. But this one's a little bit more about other topics. This is kind of an interesting parabola. It's opening, would you say upwards or downwards? Definitely upwards since it's pointing up. So this is a situation where we have an upward facing parabola. And now let's add just an extra statement here. If you said it opens upwards, then the leading coefficient A is positive. By the leading coefficient, we mean, just like in the last problem, the leading coefficient on this one was a 2. If it was a negative leading coefficient, a -2 there, this whole picture would flip around and we would be opening downwards instead. Now, once we see it's opening upwards, this is the most interesting point on the whole graph. It's the absolute minimum value, and the coordinates to this are at -4, +3. Let me double check. There we go. So that's our really interesting point on the graph, but they're not asking for that about part B. They're really referring to symmetry. And we've discussed and used symmetry a little bit when we were graphing these quadratics way back in chapter 3. The symmetry is about this line right here. It's not about that axis like the y-axis on this one, but it goes right through where the lowest point is going to be, which we'll later call the vertex. So that's our axis of symmetry. But what they want is its equation. Anyone happen to know what it would be if we wrote it out as an equation? Good call, absolutely. The x equals is the major thing about that. That's what gives us the vertical line. And then we go to the first coordinate right here. I mean, it's going right through -4. So you could also just think in terms of that value on the axis. And that's the equation. To me, this one's pretty tricky because when they say equation, what you have to put in is x equals -4 just in that way. Does that make sense to folks? Awesome. If you wrote y equals -4, then it would have been this line instead, going horizontally. So that's why there's a requirement of an x equals on that kind of problem. So this one, again, it's really not too bad when you see this topic in ALEKS. This one does go pretty fast. It's really just a run through of definitions. Next thing we're looking at is the x and y intercepts, but keep in mind, some of them don't even have x-intercepts like this one. If it opened downward and looked like this instead, then we would have found 2 x-intercepts. There would have been one right here, one right here, -8 to +2. That's what I was aiming for at least. But if your parabola is opening upwards and it's above the x-axis, for x-intercepts, all we would say is none. Which is kind of nice. We don't even have to put a number down on that one. We just have to state that. One thing about parabolas is every single parabola, no matter what, no matter how hard you try, they will always have exactly one y-intercept. So we just need to spot it on this one. Anyone see the value for y-intercept here? Exactly, it'd be right at that location. Now, if I were to put this as an actual coordinate, the coordinate of the y-intercept is put in 0 for x, and y is at 7. But ALEKS goes back and forth on this. Sometimes they want the full point like that. Other times, if they're just giving you a box, they just want the number 7. So when I grade these, I'll also keep that in mind. You can give me 7 or 0.7. I'm always going to accept both as full credit, since that's what ALEKS does as well. So we have our y-intercept. Last thing is that point right there, the vertex. Again, the vertex is the most interesting point. If you were going to plot this, you just plot the vertex, a few points on the right, and then use symmetry to get all the points on the left across the axis of symmetry. And on this graph, our vertex is at coordinates -4, 3. It's kind of hard to fit there. I'll just use arrows to show what goes where. And those are the major things about a parabola. The major thing to watch out for definition wise would be the vertex and equation of axis of symmetry. Were the major reasons for doing this problem here. Well, any questions, folks, with this graph? Yeah.
So with what you wrote at the top, about the leading coefficient,
Yeah.
You said the leading coefficient A is positive.
Mhm.
So is that variable? Where did you get the variable A from?
Oh, I wasn't really thinking of an actual variable. I was really thinking more along the lines of the A right there in standard form.
Okay,
So in this problem, A would have been 5. In this problem, A would have been a 2. And in both cases, they would be opening upwards. In fact, example 3 would look very similar to this one. It just might be on either side of the y-axis, but it would definitely be above and opening upwards.
okay.
Other questions so far? Okay, well, going off to the next concepts. Now that we have all of this, we're going to start working with this kind of information, primarily vertex, on something that just doesn't have a graph, just an ordinary function. So here's the problem that goes along with it. So if we have a quadratic function, sometimes one of the better ways to write this is, well, there's the standard form where everything is expanded out. There's a fully factored form, but there's also a vertex form. The vertex form of a parabola is extremely helpful. If you know that your vertex is, say, HK, then this is how we get the vertex form. Once I scroll to a better spot. So with a known vertex of HK, we just put K right here. Notice there is no change of sign whatsoever. And then if the first coordinate is H, coming up here, we put in a negative H. So that's a little bit tricky. Whatever happens, this one is copied from your information of the vertex. And this one is opposite sign. So if you write down a function just like this, automatically you can go down to the vertex and say it's HK right away. That means vertex form is extremely valuable. We're going to practice writing down things in vertex form. But first, I would say that this one is the challenging problem in ALEKS. If you see this problem in ALEKS, this would be a good portion of the notes to come back to example 5 to help get through it. Well, other information about the vertex form is, remember when we were taking a look at the axis of symmetry right here, all we said was it has to be x equals -4. And we were grabbing the first coordinate from the vertex. That automatically gave us the right axis of symmetry. So down here on the definition, if your vertex is at HK, your axis of symmetry is x equals h. So that's a really fast computation there once you have the vertex. And this is review information. When A is positive, it's opening upward. And if A is less than 0, the parabola opens downward. Looking at our problem, A would be less than 0. It is opening downward. So we are in this situation, in example 5. So these are the tools we need to get through this problem. And for me, this is a pretty tough problem in ALEKS. It's not so bad if you're in chapter 4. If they plot a line, we can find this equation pretty fast, get its intercept or slope. But if they give us a quadratic and 2 points, this could take a bit to get through. But it's really just a procedure. Once you get used to it, it's not so bad. Let's do this as a sequence of steps. And step 1, what I would do immediately in this process is write F in vertex form. So we ought to do that right away. One of the great values of vertex form is it's really fast for getting the equation out if you have information like this. So let's write out f of x equals a x minus h squared plus k. Our goal now is we need to find the value that should go here and the value that should go here. So that takes us now, for dealing with vertex form, we should find the vertex. Let's state it right here. Step 2, state the vertex. So looking at the graph, we should be able to see where it is immediately. We'll often write V for vertex, or we can write out as just vertex equals, but I think V is a good variable for that. It's always a coordinate, so we have to give it an ordered pair with the first coordinate, a second coordinate. And anyone see what the values should be inside here? Good call. Our vertex is either the absolute maximum or the absolute minimum. For here, it's an absolute maximum. So we'll take -3, and just plug it right inside there. We're getting through it. As soon as you have that information, we're going to plug it into the vertex form. So let's say for step 3, plug in vertex info. I don't think information will fit. Let's go with info, and then we can write that f of x is going to be equal to a quantity a times x power 2 and plus. Pretty much this is what I would write each and every time. Then go back here. If you have a vertex that's h, it'll emerge as a negative h right here. And if this was a negative h, we would have put a positive h instead. It's always going to be opposite sign to the first coordinate. So likewise, this -3, if we plugged it inside here, it'll be negative of -3. It's just going to turn into a +3 immediately. So from the first coordinate, we take the opposite. This one, we copy down directly. We just go plus a -3, or -3 would have been the better way to write that. Let's write it in as -3. So that's finally our full form. It's not the full equation because we still need to solve for that a value right there. But we're getting there, folks, step by step. Any questions so far, folks, to this step? Okay. Although it's not super relevant here, this is kind of interesting information to tie together. It came from chapter 3, which means it's something that could happen on the final exam. If we were to have plotted this, f of x equals x squared, let's make it a negative x squared, and the graph would have looked roughly like this. I'm not trying to draw it perfectly, but just generically, that's what a negative x squared would have plotted as. Now with this format here, if it says +3, this should be moving left 3. And if it says -3 here, it should be moving down 3. I definitely didn't plot it great. And it should have overlapped completely with a perfect sketch. So essentially vertex form, it's just a transformation of a function like we've already seen back in chapter 3. In fact, we've done that kind of stuff before. We just didn't call it vertex form at the moment. But that's kind of nice to know. We didn't really need it in this problem. We're just building the equation. But if you can make connections with old things from chapter 3, chapter 4, that's always a helpful thing because eventually the final exam is coming and that one will be cumulative. Well, last thing to do now is step 4. Solve for A. Once we determine what the leading coefficient is, we'll be in really, really good shape. Any questions at the moment? Okay, here's how we'd solve for A. Sorry, go ahead. Yeah.
With step 2, when you said state the vertex,
Mhm.
did you say we could choose either one of the coordinates or is there a preference of the absolute maximum and absolute minimum?
It has to be one of the absolutes. Either the maximum would be the vertex, like in this case, or the minimum would be the vertex in this case. So it has to be just specifically that point. Other questions so far? Okay, that's kind of a problem-solving strategy already on this one. If we use that point, but we never did anything with this point, that'd be kind of weird, right? A well-written problem should give you only the information you need, unless they're just trying to confuse us. So what should happen on this one is we need to focus on that point to see what's going on. It gave us coordinates -5, -11. But we can rewrite that. If we use function notation, this is really just saying that the function f evaluated at -5 returns -11. So written in function notation, that's the same thing as what this is saying. But once you do this, we're now in really, really great shape. This -5, we can do a function evaluation and place it right here where the x is. Let's connect that with a little bit of color coding. So if we plug -5 into the step 3, we're going to get a -5 plus 3 squared minus 3 equals, so all this is the left-hand side. All I've done is plugged a -5 where it's highlighted in green here, and the right-hand side is -11 coming from that point. So once we identified that this point is really just a function evaluation, and the fact that we already have a function on the table, we now have an equation in the variable a, which we can solve for. So this is what's going to give us that last portion right there, once we solve for a. So let's go and work this through. Solving for a is not too major. We just need to follow order of operations. So -5 plus 3 will give us a -2 squared. We can add +3 to both sides right away if we'd like and get -8 on the right-hand side. Now, when we square this -2, we'll get a 4. I'll write this as 4 times a. Divide both sides by 4, and a will be equal to -2. We should pause here though. We're suggesting that the leading coefficient is negative. Will that in fact make our parabola open downward, or should it make it open upward for negative? Good call. That ought to open downward, and that's encouraging, right? Because ours is opening downward as well. So at least there's a small check somewhere inside this work. Last thing we can do is, after we determine, yeah, our coefficient is consistent with opening downward, is make our conclusion. So I'll write here. Write the full function. And the answer to this will be f of x equals -2 x plus 3 squared. And I did that again, plus of -3, better to write just -3. So that's our full equation to this right here, finally. It takes a little bit of work, but with practice, if you follow these steps right here, it's really not too terrible. Just a weird kind of algebra. Yeah, go ahead. Oh, thanks for spotting that. That's like step 4, part 2 or something. Step 5. Counting gets hard at the last part of the class. Thanks for spotting that. Other questions so far, folks? Okay, so again, to me, this is kind of the nasty problem that's in section 5.1, Alex. Some of them will go really quick, but if you're having trouble getting through this, maybe, for example, you just need one more correct one before it fills up and you can move to the next topic. You're welcome to take a screenshot of the work you're working on, visit me during office hours or the tutoring center. I'll be happy to take a look at your work and say if it's correct or not before you hit submit on that and potentially have to do a couple more. So these high stake questions, I'm always very happy to give extra support on. Well, let's change this topic to the next interesting information. So if you have something that's in vertex form, that's terrific. You can identify the vertex. So for example, right here, if we were to identify the vertex, we know what it is. It's on the graph, right? But we could have said v equals, that's vertex form right here. So take the opposite of the first portion by x, that turns into a -3. Copy this portion and you get -3. So vertex form is great. If you have it, it tells you the vertex right away. But this is not in vertex form, and that's extremely frustrating. We need to put it in vertex form right here in part B. But sometimes all we want is the coordinates of the vertex. So that's what this new formula is all about. The vertex formula, I would say, is a very important formula to have memorized for our upcoming exam 2. And you might memorize it as we work through the homework set because it will get used quite often. It says if you have a parabola that looks like this, a quadratic function, it's in its standard form, not in this format we'd like, a is not 0, then the vertex is automatically located at these coordinates. That'll be the first coordinate. And to get the second coordinate, well, you just plug the first inside the function f. So it's nice to know if you have something like this, there is a way to get into vertex form called completing the square. It's not bad procedure on its own, but our textbook is focusing primarily on use the vertex formula. Honestly, that's a little bit faster than even completing the square, so not a bad approach. So what we're going to do is apply the vertex formula right away. We'll get the coordinates of the vertex, then we can write the function in its vertex form. Any questions, folks, before we start this one off? Okay, so it says that first coordinate of the vertex is automatically this, no matter what. So if our function goes 6x squared plus 2x minus 8, a good thing to write on the margin of your paper or just in your mental chalkboard is a is 6, b is 2, and c, well, I guess we don't need it, but c is -8, which is kind of weird to stop right there. Now, we're trying to find the vertex. First thing we'll do is just write x equals and state the formula. -b over 2a. Now, there is an actual really cool way to memorize this formula. Let's put it in right here just as an additional concept to help out with memorizing this one. Just going to put a little border here. Right, whether it is, there we go. So my formula goes like this. If we have ax squared plus bx plus c is equal to 0, then you can hit that with a quadratic formula, and the formula goes x equals -b plus or minus square root of the discriminant, b squared minus 4ac. That always deserves an extra color because it's extremely important. I'll divide by 2a. And here's the shorthand. The x coordinate of the vertex is as if you're deleting that part from the equation. Just focus on the -b over 2a, and you've got it. That's the right formula. So you could memorize both formulas in one shot. Quadratic formula here, and with the highlighting, that's the trick to get the first coordinate of the vertex. Does that make sense at the moment? Awesome. Now we're just going to plug in our information. So down over here, we're taking the negative of the b coefficient. So let's look those up. That'd be a -2. We're dividing by twice the a coefficient. So that's going to be twice 6. Now we can simplify right here. The 2's cancel. And this turns into just a -1/6. So we have the first coordinate of the vertex, only one more to go. So it's like we're halfway done. The formula looks bad. F of -b over 2a, it just seems really abstract, but this is all you're actually doing when you apply that formula. You take f of, well, -b over 2a is just -1/6. So we'll just throw that right inside there. So the way they have to write the formula is plugging -b over 2a inside f, but the way you would do it on paper looks totally different because you know the value of -b over 2a, you just plug it inside the function. Not a most friendly computation, but it's good practice. We'll be putting -1/6 where x is being squared, so 6 times -1/6 squared. Then it's going to be 2 times -1/6 will go right here as well. And then a -8. So let's work this through. That's a power 2 there. Let me actually fix that. It looks kind of funky. So here we're going to get 6 times, we square this, it's going to be 1 over 36. This will reduce to 1/6. Because of that, I'm going to leave this one as a -2/6 without reducing. And then a -8, let's make it be over 1. I'll try to force everything to have a denominator of 6 as we work through this. So first, let's do a cancellation. That just turns into a 6 down below. And so now we have 1/6 minus 2/6. Here, multiplied by 6 over 6 minus 48/6. And we get -49/6. Sixths is hard to say, it seems like, but there's our value altogether. And that's our second coordinate of the vertex. Well, finally, when it says find the coordinates of the vertex, the expectation is our end answer would be written this way. V equals first coordinate of -1/6 and second coordinate of -49/6. So the claim is that's exactly where the vertex would be located. That would be really tough to find. Even if I plot this, even if I plotted on Desmos and zoom in really, really well, I'm probably not going to find -49/6 exactly. I'm going to get some decimal expansion. And that's the value of this formula. It's telling us the vertex exactly. Well, just for extra information, that leading coefficient is positive. So this graph, if we were to graph it, would look like this. That means the vertex is going to be the coordinates of the minimum point on that entire graph. It'll be at -1/6, -49/6. Well, that's a vertex formula. We're going to be using it here and there on the rest of these notes. But first, any questions, folks, on using it here?
I think you get the 48 or -48/6.
What I did with that one was I was trying to get a denominator of 6 all the way through. So I went times 6 here and times 6 here,
Okay.
just to force that right denominator. Other questions at this so far? Okay, well, finally, now that we have all the information about the vertex, we can take F, write it in vertex form really, really fast. There is one extra trick that we would need though. Let's start off by saying the leading coefficient of F is, anyone spot what its leading coefficient should be? Exactly. It's going to be the coefficient, the numerical part of the term that's associated with a degree 2, the x squared. So our leading coefficient is 6. That one's kind of tricky. I mean, just in our last problem, it took us a while to find the leading coefficient, the -2 right there. But once we found it, we just stuck it right here in its vertex form. We're going to use that same strategy again and say f of x is equal to 6. Then we'll open a parenthesis, put x here with the power 2, and we have to place 2 values. A number should go here and here. They would see what ought to go into that first blank. It wouldn't be -2. It has to come from the vertex somehow. Oh, no worries. Exactly. So the trick is, the moment you have your vertex, take the opposite of that first coordinate. That's tricky enough that let's make a note about it right here. Take opposite sign going in. And so now we have the value here. It's going to be plus 1/6, just like you said. Then the next thing, which is tricky, we go to the vertex again, we go to the second coordinate, but this one's just copied in directly. So I'll put a little arrow here, and my note will be copy. So there's a sign flip arrow, always the first coordinate, and there's a copy arrow, always the second coordinate. This becomes -49/6. So if we did everything correct, that's finally the vertex form for this polynomial. This one is kind of tough in ALEKS, but what makes it not so bad is that there's always an immediate check in this process. First, before we look at that check, any questions at the moment? Okay, so if you're working through ALEKS, if this one's kind of tough, I encourage you to give this a try. Pick out your favorite graphing calculator software. I'll use Desmos. And if that's the right format, here's what you should be able to do. I'm going to go to the original function f. Here it is. Let's plot that. Just write it in verbatim. F of x equals 6x squared plus 2x minus 8. So there it is in all its detail. Notice the vertex is at a really odd position. That's the -1/6, -49/6 that we're seeing right there in decimal form. And my check is, we plot this function, f of x equals whatever it is, it ought to look exactly the same. So 6, x plus 1/6. The moment you square it, the line becomes a curve. And when I did this earlier today, I made a mistake. I found -51/6. It looked about right until you zoomed in just a little bit. Not quite right. But if you have the exact value of 49/6, no matter how much you zoom in on this, it's only going to look like one curve. So this problem is pretty tricky, but it's nice to have an immediate check in software. Any questions, folks, on finding that vertex form or anything else at the moment? Okay, well, with the vertex form in play, we could do a couple things that are not so bad. We also want the x-intercepts. And there's two ways to do it. You could go up here and try to see if that's going to factor. You could take a look at the discriminant, maybe use the quadratic formula, or you could take a look at your graph as well. It looks like there's an intercept right here at 0. Yeah, it's kind of interesting. Goes right through the origin. But there's another one here, and I don't know what it is. We need to find its exact value. So here's what we could do to make that all happen. We want to find the x-intercepts. Then an x-intercept is always found by doing this. You take f of x, set it equal to 0. If that feels like deja vu, then that's good. We're finding the zeros of the function, which is the same thing as saying we're finding the roots of the function. But this time we're looking for x-intercepts specifically. What I mean by that is if we compare with earlier work, this one had no x-intercepts. We got complex values, but we were still finding the zeros. So we set f of x equal to 0. It says find x-intercepts. You're still just doing that same thing. That's almost kind of crazy in a way. It feels like there's 3 concepts going into one kind of procedure right here. And now you have options. You can either grab that f of x, the one in standard form, but actually the easier way is to grab this one, the one where we already complete the square. Let's try it out this way. If you don't like it, no worries. You can always hit that with the quadratic formula. It's always just going to work. This will just be an alternative method. So where f of x is, I'm going to copy in the vertex form. 6 x minus 1/6 power 2 minus 49/6 and set it equal to 0. Now, if you're solving this kind of equation, first thing you'd want to do is isolate the part that's being squared. So we would add 49/6 to both sides. We get 6 x minus 1/6 squared equals 49/6. Yeah, go ahead. Oh, that's a great question. I think I just miscopied. That absolutely should have been a plus 1/6 coming from up there. Let me just kind of overwrite it like this to show that mistake. Might look cleaner if I go plus 1/6 and plus 1/6 below. Thanks for capturing that. You were going to get a strange result without that correction. Other questions so far? Okay. Well, next thing we can do is, well, we could divide both sides by 6, right? That would do the job. We will get an x plus 6, excuse me, x plus 1/6 squared equals, if I divide by 6 here, that 6 is gone. Divide by 6 here, and we'll get 49/36. So far, so good. Next thing to do is take the square root of this equation. If you square root both sides of this equation, well, it'll look like this to start out. X plus 1/6 squared. Oh, and I want a square root. Let me change that to an actual square root. Equals 49/36 square rooted. I left some space here because I would make a mistake if I left it just like this. Anyone see what needs to go right where that red dot would be? Exactly. If we take square roots of both sides of the equation, there's in fact 2 potential answers. And this is always really easy to miss. The 2 potential answers can be tracked with a plus or minus. And we ought to expect that because if we use the quadratic formula, that's where the plus and minus emerges, right there. We're just using an alternate procedure. We're not eliminating the 2 possibilities. So now, finally, this turns into There's a cancellation with the square root and the power 2 right here. It's just x plus 1/6. Here, we can't eliminate the plus or minus, it's baked into the problem. But the square root's nice. The root of 49 is 7. The root of 36 is 6. And this would be the result we get here. So we're getting closer, but now the plus and minus, there's really two possibilities. First, let's subtract 1/6. There's 1/6 plus or minus 7/6. And we're just about there at our answer. So first, let's imagine we're dealing with just the plus. We would take 7/6 positive minus 1/6. That would give us a 6/6 for a value of just a 1. Does that make sense, folks, on considering the positive root right here? Yeah, go ahead. Right here or earlier?
The last step before you go x equals 1.
Oh, so this portion.
Yeah.
Oh, gotcha. What I was doing was just subtracting 1/6 right here from both sides. So that's what produced the negative 1/6 in that location. Other questions at the moment? Okay. Well, we get a 1 when we use the positive root. Now let's change gears and analyze the negative root. Now it's negative 1/6 minus 7/6. That would give us a negative 8/6. Let me actually write it down here. Negative 1/6 minus 7/6. Lots of sixths today gives us negative 8/6. But when we reduce that, we get negative 4/3 dividing by 2 into numerator denominator. So it's 1 and a negative 4/3. We got it, folks. Those are the two x-intercepts in this problem. You know, actually looking at this work really closely, it's not bad the procedure we took. We took that equation set to 0. This is what it looks like to solve. But I might take back what I said earlier. The quadratic formula might have been just as fast, maybe even a little bit faster on this one. Would you all like to see it with the quadratic formula, or do we feel okay with this version? All right, let's give it a try. Awesome. So if we want to try this again, let's call this method 1, just so the notes are readable. It'd be weird to see why we're doing it twice. And now we're going to do method 2 using quadratic formula. Just really for the sake of practice. You know, you might not have to use a quadratic formula. If you're getting these values right here, you should be able to just factor this equation and work in that type of way. Let me copy this down below, and kind of hide that. So method 2, we're going to try out the quadratic formula. But if you're a fan of factoring, that's probably the fastest thing you could have done on this problem. But the purpose of section 5.1 is to get familiar with these ideas, so not a bad thing to practice. If we're using quadratic formula, I'd immediately start with this. The discriminant, b squared minus 4ac. Our b coefficient is the middle one, the 2. So we'll have a 2 squared minus 4 times a is 6. And c is negative 8. So this is now turning into a 4. Plus, because we have 2 signs, oh geez, 6 times 4 is 24 times 8. That's getting really, really large. Let's let Desmos help us with that one. So I have 4 by 6 by 8. So that turns into a positive 192, which is going to be 196. Well, if it has these as x-intercepts, which are ordinary integers, there's no square root of 5, no square root of 2, there's no complex number, that must be a perfect square. So something times something is 196. I'm not sure how far my memory goes on that. Maybe it's 13. Yeah, oh geez, almost my dyslexia tricked me on that one. That's 169. Let's just keep going down the line. It was the next one, 14 squared. So our discriminant is a perfect square. Let's write that out. So now in the quadratic formula, we're in business. We can say x equals let's just state the formula. So we're practicing it. We don't want to just rip through it. So here's the statement of the formula. And one great strategy for exams, if you copy this formula down and the vertex formula down every single time you use it, you will memorize it. I promise. By the time you get through ALEKS, it's just going to be burned into your brain at that point. So we'll go next and write negative b here is going to turn into a -2. Plus or minus the square root of 14 squared. That's just going to turn into a 14. So that should resolve really quick. The denominator is twice a, and our a coefficient is 6. So twice 6. Then as we go to simplify this, it now becomes -2 plus or minus square root of perfect square, and you'll just get the 14 itself. Divide by 12. And hopefully we get to +1, -4 thirds. Let's see what happens. I'm going to split this off into 2. X equals -2 plus 14 twelfths. So I'm focusing on the positive root. It's going to give us 12 twelfths, which gives us a 1. Hey, we've got that at least, so that makes us happy. Let's try this again. If we use the negative root, x would be -2 minus 14, divide by 12. So -16 twelfths, we can divide by 4 above and below, or yeah, let's go -4 thirds if we divide by 4. And that gives us the second root that we found. So I think it's kind of a matter of preference that now doing it twice. I think a lot of people are going to prefer the quadratic formula. It's hard to go through the United States education system without being exposed to this thing. And some people might find that this is just as easy. Or the best method was to know that that could factor and just try to factor it. That might have been the best thing to do to get those values. Well, any last questions, folks, on finding those intercepts by either method? Okay. If you're told to find zeros or find roots or find x-intercepts, you're just doing that. But here's the good news. If you're told to find a y-intercept, you know what? That's a good problem. It goes like this. At a y-intercept, I'll write y-int for intercept. X itself is what turns into 0. So if we go back to our original function, here it is recopied again. This is literally all you have to do to find a y-intercept. Take the function, write f of 0. So we did it. We set x to 0 immediately, and we get -8. The y-intercept is fantastic because it's kind of just staring right at us. If you plug in a 0 for x, you've wiped out 6x squared, you've wiped out 2x. The intercept itself is right at -8. So we can make a conclusion. The y-intercept equals -8. Or as a coordinate, it would have been 0, -8. Phew, it's kind of nice to have an easier problem. Now, last thing we're going to do in part E is put all this information together and sketch the graph of that. Any questions or comments first before we try this out? Okay. The graph doesn't have to be too fancy. We've done these kinds of graphs before. What I would do to get a really fast graph is just put down the coordinates that are easy to put down. Y-intercept at -8 is not so bad. So 1, 2, 3, 4, 5, 6. I was worried about that. Let's get a better, bigger spot for this. First thing I'm going to put down is just that -8. So 1, 2, 3, 4, 5, 6, 7, 8. Down there is where we're going to have our y-intercept. Next thing I will do is take the x-intercepts. Let's plot these both. We have an x-intercept at +1 exactly. So right here. And we have another one at an awkward location, -4 thirds. So here's -1, -2. -4 thirds would be about there. It's -1 and a third. So it's really just off to the left. And we do have one other piece of information. Let me scroll back up to grab it. This problem is a bit long. As an exam question, this is really like 3 different questions all glommed into one. I'll never ask one question this long, more for the sake of notes. But here's our vertex finally coming down. This one is really hard to plot. -1/6, that's just barely to the left of the origin, and -49/6, well, let's see. If it was -42 or -48/6, that would have been -8. This one is already at height, -8, so this goes just a little bit lower than the intercept and just a little bit to the right. It's essentially right here. That's my best ability of plotting that location. So the vertex was essentially kind of useless, except we know that it dips to its lowest point right there. And to sketch the graph of F, it's a little bit tricky, but let me give it a try. It's very steep. And it comes through like that. Kind of an ugly graph, but he'll do the job. Desmos did a little bit better with it. Where'd it go in Desmos? It's just disappeared. I forgot we changed that out. But finally, that's the whole graph of this function. I would say the important features of this one is really knowing how to take a function like this, find its vertex, and get it into vertex form. I would say that's the major takeaway with this. And we did everything else just to practice intercepts, X and Y, on the last couple parts. Finally, just because we can, we put it together, and there's our plot. Oh, dang, and there's still more to do. We also want a domain and range. Geez. Let's finish out this last part. Domain. Not too bad. This is a polynomial. So anyone see what it ought to be? Yeah. Exactly. Sorry, say again. Gotcha. So for this one, I think that's the kind of major reason why sometimes we put arrows on these. It's going up and to the left forever, so -infinity, up and to the right forever, so -infinity there. For the range, I did bring the vertex back. The range is a little bit tricky. It's going to start at the lowest point, which is right here, but that was at, well, what value should I use? -1/6 or -49/6? Good call. It should be the lowest point right here as a second coordinate. For range, it's just the second coordinate we care about. So -49/6, that's the lowest point. But then it goes up forever. So we'll go comma infinity. We've also done this one in chapter 3, but what we didn't do in chapter 3 was actually calculate our vertex. They always gave us it on the graph. So now we see how the vertex gives us a range as well. Well, I think we're at a good stopping point for folks. We didn't finish the notes. I still have a warm-up problem and then a word problem down below. So we'll finish off these when we come back on Tuesday's class. Any last questions or comments then before we call tonight? Okay, well, have a great weekend, folks. Don't work too hard, but if you have questions, I'll be available in room 220 after this.
One question about the.
Mhm.
It'll go through negative.
Oh, absolutely. That was my mistake on that. Negative to positive. Absolutely. Alex would have absolutely marked that incorrect without a positive there.
Okay, I saw it, I was like, how's that? So I was just.
Thanks for mentioning that. You've got it on the video and you've got it on the notes. So that's a good correction to keep.
Yeah.